Today we're going to take a look at another integration method called substitution. Substitution is basically the way that we do the reverse chain rule. And this is going to take some creative looking at with our process. You're going to be able to need to recognize the structure of this type of a problem. But to set it up, I want to recall when we were asked to take the derivative of something like 2x cubed plus 1 to the 5th power. The way we took that derivative is we took the derivative of the outside, bringing the 5 out front, 2x cubed plus 1 to the 4th power, and then we multiplied by the derivative of the guts, which was 6x squared. And what we saw in here is we can see part of the problem, this last part, is the derivative of this stuff, the 2x cubed plus 1. The derivative is part of the solution. So when we're taking the integral, we might recognize that the derivative is part of the integral. And the way we're going to do that is we're going to use a substitution to make the problem easier to work with. We are going to let u equal, we're going to say, I'm going to call it the main function. It comes from, maybe you might say, the complicated part. And then du is going to represent the derivative of u. And our goal is that this derivative is part of the problem. Because if du is part of the problem, we can simplify it down to a much easier integral. Let's take a look at an example where that happens. Let's do the integral of 6x times 3x squared plus 4 to the 7th power dx. I want to notice that there is a derivative inside this problem. Notice the 3x plus 4, the 3x squared plus 4. The derivative of 3x squared plus 4 is 6x. When we see that relationship, we're going to let u equal the complicated part, the 3x squared plus 4. That's our u. Du then is going to be equal to the derivative of u. The derivative of u, just looking above, is 6x. And then we're always going to have a dx as part of that. And so what we see is this 6x dx is going to become du. So now my integral is the yellow part, u to the 7th power. The 6x dx all gets crammed into what we're going to call du. And so you see the same structure of a problem with this, what's called u substitution. We have replaced the 3x squared plus 4 with u. All of that's raised to the 7th power. And the 6x dx is the derivative of u that gets replaced with du. This integral is now much easier to solve. We solved this yesterday. That's u to the 8th times 1/8 plus a constant. But we don't really care about the u we need to change it back to x, and that's where we go back to our substitution step where we said u is 3x squared plus 4. So we'll replace our u with that, and we get 1/8 times 3x squared plus 4 to the 8th power plus a constant, and we now have the antiderivative, or the integral, of our problem. This process feels a little clunky at first. It takes a little bit of practice to get a hang of, so let's do several examples here today. How about we do this example? Let's do the integral of 3 dx over the square root of 3x minus 5. This would be really difficult under normal circumstances. With substitution, though, it's going to become much easier. Notice the complicated part under the square root is 3x minus 5. And we see the derivative of 3x minus 5 is 3 dx. We see the derivative inside the function. So we're going to let u equal the complicated part, the 3x minus 5. Du is going to be its derivative, which is 3 dx. And now we can make a substitution, replacing 3 dx with du, replacing the 3x minus 5 with the u. And now the equation becomes the integral, and I'm going to make the square root u to the negative 1/2, because the square root's 1/2 power and it's in the denominator, du. And notice the u replaces the 3x minus 5. The du replaces the 3 dx. And now we can integrate this quite quickly because we know we just increase the exponent by 1 and multiply by the reciprocal, adding a constant. Of course, we don't really care about u. We want to change it back to x's, and we have that with our u equals equation. So for our final answer, we have 2 times 3x minus 5 to the 1/2 power plus a constant. We now have taken this antiderivative. Now, sometimes when we're trying to find the derivative inside the function to make substitution work, we can get close but not quite there. Sometimes what we're missing is just a constant or a number out front. We've got everything else, but maybe the number 7 needs to be there, and it's not there. Well, fortunately, with integration, we can create constants that we need to make the problem work out if we do it correctly. If we need a constant, we can multiply it inside the integral if we also multiply by the reciprocal outside. Here's what I mean by that. Let's say we're doing the integral of x squared times the square root of x cubed plus 1 dx. Now we might be inclined to see this x cubed plus 1 as our u. I'm sorry, x cubed plus 1 as our u. If that's the case, du, the derivative of that, is 3x squared. So we've got our u, we've got our du is 3x squared dx. The problem is we only have x squared dx. X squared dx. We don't have that 3. So where we're going to get that 3, because we're only off by the constant number 3, is we can multiply by a 3 inside the integral if we also multiply by its reciprocal outside the integral. Because you notice those 3's under normal circumstances would divide out and go away. So we really haven't changed the value at all. But what we have done now is we've introduced the number 3 to make the integration and the substitution possible. So now we have 1/3 outside times the integral of the square root of the stuff becomes u to the 1/2. And the 3x squared dx becomes du. And now we can evaluate this. That was supposed to be green. I'm going to make it green again, just to be consistent. We've got 1/3 times the integral of u to the 1/2 du. And so in orange, we can solve this by adding 1 to the exponent. So we now have 3/2 multiplying by the reciprocal, which is 2/3, times we've got that 1/3 out front plus c. When we multiply those fractions straight across, we get 2/9 u to the 3/2 plus c. But again, we need to get back to x's, so we go back to the u equals step, and we see that our final answer is going to be 2/9 times x cubed plus 1 to the 3/2 power plus a constant. This type of substitution is going to be more common for us, where we have to do a little bit of work to get that constant to work out. Everything else will work out fine. But if we need a constant, we need to multiply inside the radical and the reciprocal outside of the radical. Don't lose that reciprocal outside of the radical, though. That is a key part of it. So let's say we want the integral of x plus 3 over x squared plus 6x squared dx. And what we might notice is we've got this complicated stuff squared. So that's probably going to be our u, the complicated stuff, the x squared plus 6x. So if we make that our u, our du is 2x plus 6 dx. Notice, though, we've got x plus 3 dx. Well, fortunately, we can get that x plus 3 to turn into 2x plus 6. Notice if we factor out a 2, that's 2 times x plus 3 dx. We're really just off by a constant of 2. So we're going to multiply by 2 inside the integral, and the reciprocal 1 over 2 outside of the integral. So now we've got 2 times x plus 3 dx as the inside guts of the integral. So now we have 1/2 times the integral of all the 2x plus 3 dx becomes du. The 1 over x squared plus 6x squared is now u to the negative 2 power. And this is really easy to solve from here. Increase the exponent by 1, multiply by it on the outside, or divide by it, makes it negative 1/2, plus a constant. And again, we go back up to the u to get our x's back, and we have negative 1/2 times x squared plus 6x to the negative 1 plus c for our final integral. Well, for our final solution, I should say. Let's try another one. Let's do the integral of 4x minus 10 over x squared minus 5x dx. Again, the more complicated part this time that we can work with is that x squared plus 5x. We're going to make that equal to our u. Oops, it's minus. Which means du, the derivative of that, is 2x minus 5. So we've got our u. Our du we want is 2x minus 5, though. We have 4x minus 10. Do those vary by a constant? They do, because you might notice in that numerator, if we factored out a 2, we would have 2x minus 5. So there's the constant dx that we want. Need to have a dx. We just have this pesky 2 in the way. And so to get rid of the 2, we can multiply by 1/2, fixing the constant. But if we multiply by 1/2 inside the radical, we're going to have to multiply by the reciprocal, which is just 2, outside of the radical. That way the 2's will divide out, and now we have the exact form that we want. We have 2 times the integral of 1 over u du, or you might have said 2 times the integral of u to the negative 1 du. Remember, the integral of 1 over u, or u to the negative 1, we can't just increase the exponent by 1 and divide by it, because then we would be dividing by 0. So we have 2, but we do know the integral of 1 over u is the natural log of u plus c. Then to get our x back, we go to that u equals equation. And so we have 2 times the natural log of x squared minus 5x plus a constant. And we have our final solution. Let's try another example. Let's do this one. Let's do the integral of x to the 4th e to the x to the 5th dx. Now we know the derivative of e to the stuff. We've just got the stuff of x to the 5th. That's really the complicated part. U equals x to the 5th. Then du would be its derivative, 5x to the 4th dx. So we've got the x to the 5th. The du, right now we've only got the x to the 4th dx. We need to get a 5 in there. So we multiply by a 5 inside the radical and a 1/5 outside of the radical. And now we've got that form that we like to see, the 5x to the 4th dx. Which means now our integral is 1/5 times the integral of e to the u. Notice the e is still part of the problem. It's only the exponent that's become u. And then the 5x to the 4th dx becomes du. And this is a really easy integral for us to take. The integral of e to the u is e to the u with a 1/5 out front plus c. And again, we need to get that u back, so we go back to the u equals, and we have 1/5 e to the x to the 5th power plus a constant for our final solution. So this is the pattern that we want to follow for all of our problems. Let's kind of summarize number 4. In general, to make these problems simpler, we make u equal, you will have noticed our first bunch of problems, we made u equal to the stuff under the radical, or we made the u equal to the stuff raised to the exponent, that yellow part. U, in general, the most common place we're going to use it is we're going to make it equal to the stuff under a root or an exponent. We also saw in example C, we made u, the yellow part, equal to the stuff in the denominator. So another option is you can make u equal to the stuff under, I'm going to say in, the denominator. And the third place we've seen the use of u is in example D. We made u equal to the stuff in the exponent. The key that we need to look for when we make it equal to the stuff is the derivative of the stuff must be in the problem. Or missing a constant. You know, if it's missing a constant, just a standalone number like a 7 or an 8 or a 1/2, we can get that in there by multiplying by the reciprocal. But if that stuff is in there, we can use substitution to evaluate the integral. Now there is one other little tiny trick that we can do with integration and substitution that I want to show you that doesn't quite follow these rules, but it's a slick little trick to take the derivative. If the derivative is not in the problem, creative substitution may still work. I'm going to say may still work because this might not necessarily work perfectly. But if it does, it's nice. Let's say we're doing the integral of x times the square root of 1 minus x dx. And when we see that stuff under the radical, we're inclined to make that stuff equal to u, 1 minus x, which means du, its derivative, is going to be negative dx. Maybe negative 1 dx, if you want to say that. And we do have that 1 minus x in there. The problem is we also have this quirky x. Here's where we get creative. If u equals 1 minus x, and we add x to both sides, well, actually, what I should say what we're doing is we're going to solve for x. We're going to see what that quirky x is equal to. And the way I'm going to solve for x is add x to both sides equals 1, and then subtract the u from both sides. So x is equal to 1 minus u. So that quirky x, we're going to make equal to 1 minus u. Now for the du, we still need to fix the fact that we need a negative dx, and right now everything's positive. So if we multiply by negative 1 on the outside, divide by negative 1 on the inside, that just makes it negative. we now get that dx part, that negative dx that we need to make our substitution. So this substitution actually has 3 parts to account for the random extra x. The first part's the u, which is 1 minus x. The second part's the du, which is the negative dx. We had to make the constants work for that. And the third part is that extra x. And we just solved the u for the x part. And now that we've done that, what we have is the integral, negative, because we had to do that to make everything work. The x becomes 1 minus u. Then we've got the square root of the stuff, or u to the 1/2, du. Well, this doesn't look much easier to solve anyways. Well, it is if we distribute that u through the parentheses. So we have negative integral 1 times u to the 1/2 is u to the 1/2 minus u to the first times u to the 1/2 is u to the 3/2 du, and we can take this integral. We have negative, don't lose that negative, u to the 3/2 times the reciprocal 2/3 minus u to the 5/2 times the reciprocal 2/5 plus c. I'm going to go ahead and distribute that negative through. So we have negative 2/3 u to the 3/2 plus 2/5 u to the 5/2 plus a constant. And now, just like before, we're going to go to that u equals, change it back into our x's. So for our final answer, negative 2/3 times 1 minus x to the 3/2 power plus 2/5 times 1 minus x to the 5/2 power plus the constant c. And with some creative substitution, taking care of that extra x, we have found our antiderivative. We have integrated this expression. This 3-part substitution is a really neat, slick trick. So let's do it one more time to make sure we are really good at it. Let's do the integral of 4r times the square root of 8 minus r dr. Again, what we notice right away is that 8 minus r under the square root is a good candidate for our u, the complicated part. 8 minus r, that's all accounted for. Du, then, the derivative, is going to be, again, negative 1 dr. So we need to get negative 1 dr. Right now we've got a 4 and a dr. So the way we make 4 into a negative 1 is we're going to multiply by negative 1/4. When we multiply by negative 1/4, the 4's will go away and we have that negative 1. If we multiply by negative 1/4 inside, though, we have to multiply by the reciprocal outside, which is negative 4. Now we've got that negative 1 dr. The negative 1 dr. that catches in this problem, we also have this extra pesky r. So to account for that, we're going to solve our u equation for r. We add r and subtract u, we get r is equal to 8 minus u. And so this is going to be the substitution made for that extra pesky r. We now have negative 4 times the integral of the r becomes 8 minus u. The square root of the stuff becomes u to the 1/2. And the negative 1 dr becomes du. Now we're ready to solve. First, by distributing the u through to make it something we can actually take the integral of. So we have 8u to the 1/2 minus u to the 3/2 du. Then we have -4 times u to the 3/2 times the reciprocal 2/3 times 8 minus u to the 5/2 times the reciprocal 2/5 plus that constant. And we have a little bit more algebra this time to clean it up, but it's not too bad. Multiplying the 4 through, we've got -4 times 8 is -32 times 2 is -64 over 3 u to the 3/2 plus 4 times 2 is 8/5 u to the 5/2 plus a constant. And now all we have to do is go back to those r's with that u equals 8 minus r step. And so for our final answer, we have -64/3 times 8 minus r to the 3/2 plus 8/5 times 8 minus r to the 5/2 plus a constant. It's ugly, but that's okay because it is the correct final answer using our integration by substitution technique. Integration by substitution really is going to take practice to help you identify what part of the function is the u, and do I have the du I need in order to do the integral. Practice identifying the parts you need before you come to class. The difference between the master and the beginner is the master has failed more times than the beginner has even tried. If you're watching this video and seeing that, oh, the video identifies that u so quickly, so easily, it's not too bad at all. It's because I've done thousands of these. You have not. So you need to practice so you can start to identify how the substitution works. Do those problems before you come to class so that you can come to class with questions and we can answer those questions. It's not a difficult process, but it is one that takes practice in order to recognize. Take a look at the homework. Practicing your substitution. See you in class tomorrow.